You are not touching anything right now. The feeling of pressure where your body meets a surface, that is not contact. That is repulsion. The electrons in your body refusing to let anything get close. Everything you have ever held, sat on, or walked across has maintained an infinitesimal gap from you at all times. Physics is not the study of things. It is the study of the impossibly strange rules that make things look normal, and almost none of it works the way you think it does. Here are 20 facts about physics that will make you question whether anything you experience is actually real. You never touch anything. The sensation of touch is entirely electromagnetic. When you press your hand against a table, the electrons on the surface of your hand repel the electrons on the surface of the table. They never actually make contact. The feeling of solidity, resistance, texture, all of it is the force of repulsion between electron clouds. You have never touched another human being. You have never held anything. Every physical experience you have ever had has been mediated by an invisible force field operating at distances too small to see. The same force that holds electrons in orbit around atoms is the same force giving you the sensation of sitting in a chair right now. Atoms are almost entirely empty space. If you took a hydrogen atom and enlarged the nucleus to the size of a marble, the electron orbiting it would be roughly a kilometer away. Everything in between is empty. This means that every object you have ever seen, every mountain, every building, every human body, is almost entirely nothing. The reason solid objects feel solid is not because they are full of matter. It is because of electromagnetic repulsion between those vast emptinesses. If you could somehow compress all the actual matter in every human being on Earth, removing the empty space, all 7 billion of us would fit into a space roughly the size of a sugar cube. Time slows when you move. Einstein's special theory of relativity, published in 1905, proved that time is not a constant. It passes at different rates depending on how fast you are moving. The faster you travel relative to someone else, the slower time passes for you. This is not theoretical. The GPS satellites orbiting Earth move fast enough that their clocks run slightly slow compared to clocks on the ground, by about 7 microseconds per day. If engineers did not account for this difference, your GPS would drift by roughly 11 kilometers per day. Every time you navigate using your phone, you are relying on a correction calculated from Einstein's equations. The double-slit experiment: fire a single electron at a barrier with 2 narrow slits, and something impossible happens. The electron passes through both slits at the same time and interferes with itself, creating a wave-like interference pattern on the detector behind. The electron behaves like a wave. But if you add a detector to observe which slit the electron actually goes through, the interference pattern disappears. The electron suddenly behaves like a particle. The act of observation itself changes the outcome. Physicists have run this experiment thousands of times in dozens of variations. The result is always the same. Something about being measured forces a quantum system to commit to a single state. No one fully agrees on why. Heisenberg's uncertainty principle in 1927. Werner Heisenberg proved something deeply unsettling. It is physically impossible to know both the exact position and the exact momentum of a particle at the same time. The more precisely you pin down where something is, the less precisely you can know how fast it is moving, and vice versa. This is not a limitation of our instruments. It is a fundamental feature of reality. The universe itself does not contain both pieces of information simultaneously. Before measurement, a particle does not have a precise position. It has a probability distribution. The act of measuring creates a definite value where none existed before. Quantum tunneling. Quantum mechanics allows particles to pass through barriers they should have no energy to cross. In classical physics, a ball rolling toward a hill will stop if it does not have enough energy to climb over. In quantum physics, a particle hitting a barrier has a small but real probability of simply appearing on the other side, as if the barrier were not there. This is not hypothetical. It is the mechanism by which the sun generates energy. Inside the sun's core, protons do not have enough energy to overcome their mutual electromagnetic repulsion and fuse. They quantum tunnel through the barrier. Without this effect, the sun would not burn. Stars would not exist. The universe would be dark. Quantum entanglement. Two particles can be entangled, meaning their quantum states are correlated, regardless of the distance between them. Measure the spin of one particle, and the other particle's spin is instantly determined, even if it is on the other side of the galaxy. Einstein called this spooky action at a distance, and believed it meant quantum mechanics was incomplete. Decades of experiments, culminating in the 2022 Nobel Prize in Physics, have confirmed entanglement is real. The correlation is not explained by hidden information the particles carry with them. Something genuinely non-local connects them. Entanglement cannot be used to send information faster than light, but it underpins quantum computing and quantum cryptography, technologies being actively built right now. E equals mc squared. Einstein's most famous equation says that mass and energy are the same thing, just in different forms. A small amount of mass is equivalent to an enormous amount of energy. The conversion factor is the speed of light squared, which is roughly 90 quadrillion. This means that converting even a gram of matter entirely into energy would release the equivalent of 21 kilotons of TNT. Nuclear weapons work by converting a fraction of a percent of their mass into energy. The sun converts about 4 million tons of mass into energy every single second. Mass is not a fixed property of matter. It is stored energy. The distinction between stuff and power does not exist at the fundamental level. Gravity bends light. Newton's theory of gravity described a force acting between masses. Einstein replaced it with something stranger. Gravity is not a force at all. It is a curvature in space-time. Massive objects bend the fabric of space and time around them, and other objects follow the curves. One consequence is that light, which has no mass, still bends around massive objects. In 1919, during a solar eclipse, Arthur Eddington photographed stars near the edge of the sun. Their positions were shifted exactly as Einstein had predicted. Light was bending around the sun. The observation made Einstein world-famous overnight. We now use gravitational lensing to map dark matter and observe galaxies billions of light-years away, by using the gravity of closer objects as a natural telescope. The Higgs field. For decades, physicists had a problem. Their equations describing fundamental particles worked brilliantly, but only if particles had no mass. Mass had to be added by hand as an unexplained assumption. In 1964, Peter Higgs and others proposed a solution, an invisible field that permeates all of space. Particles acquire mass by interacting with this field. The stronger the interaction, the more massive the particle. In 2012, after 50 years of searching, and a machine the size of a city built specifically to find it, scientists at CERN detected the Higgs boson, the particle associated with the Higgs field. Mass is not a property particles carry. It is a resistance they experience as they move through an invisible medium that fills the entire universe. The vacuum is not empty, according to quantum field theory. Empty space is not empty. It seethes with virtual particles, pairs of particles and antiparticles that spontaneously pop into existence and annihilate each other almost instantly. These virtual particles produce measurable effects. The Casimir effect, demonstrated in laboratories, shows that two uncharged metal plates placed extremely close together in a vacuum are pushed together by the pressure of virtual particles outside the gap that cannot fit between them. The energy density of the vacuum is one of the biggest unsolved problems in physics. Calculations predict it should be enormous. Measurements find it is almost zero. The discrepancy is roughly the largest error in the history of science, and no one knows why. Entropy always increases. The second law of thermodynamics states that the total entropy of a closed system, a measure of its disorder, can never decrease. It can stay the same, or it almost always increases. Ice melts. Coffee cools. Perfume spreads through a room. These processes never spontaneously reverse. Why? Because there are astronomically more ways for energy to be disordered than ordered. The probability of disorder spontaneously decreasing is not zero, but it is so vanishingly small it has never been observed. This is also why time seems to have a direction. The laws of physics are almost entirely symmetric in time. They work equally well run forwards or backwards. The second law is the reason you experience a past and a future rather than both equally. 65 billion neutrinos pass through you every second. Neutrinos are subatomic particles produced in enormous quantities by nuclear reactions in the sun. They have almost no mass, carry no charge, and interact so weakly with matter that they pass through almost everything. Every second, roughly 65 billion solar neutrinos travel through every square centimeter of your body, whether it is day or night, whether you are in a basement or on a mountaintop. The Earth itself barely slows them down. To have a 50% chance of stopping a single neutrino, you would need a wall of lead roughly 1 light-year thick. We detect them by building tanks containing hundreds of tons of ultra-pure water in deep mines and waiting for the rare occasion one hits something. Gravitational waves are real. In 1916, Einstein predicted that accelerating masses should create ripples in space-time, gravitational waves spreading outward at the speed of light, stretching and compressing space as they travel. For a century, no one could detect them because the effect is almost inconceivably small. In 2015, a pair of detectors called LIGO measured a distortion in space-time shorter than 1,000th the diameter of a proton, caused by two black holes 1.3 billion light-years away colliding with each other. The signal lasted a fifth of a second. The machines that detected it are the most precise measuring instruments ever built. Gravitational wave astronomy is now a new way to observe the universe, one that does not use light at all. Nothing can reach the speed of light according to special relativity. As an object with mass accelerates, it becomes harder to accelerate further. The faster it moves, the more energy is required to push it faster, because its effective mass increases. To reach the speed of light, you would need infinite energy. This is not an engineering problem. It is a mathematical impossibility built into the structure of reality. The speed of light is not just a speed, it is the maximum rate at which any information or causation can propagate through the universe. It is the reason the past cannot affect the future faster than light allows. It is why there are regions of the universe that are permanently unreachable, and events that can never affect each other. Black holes are slowly evaporating. In 1974, Stephen Hawking combined quantum mechanics with general relativity and discovered something no one expected. Black holes are not completely black. Due to quantum effects near the event horizon, pairs of virtual particles spontaneously appear at the edge of a black hole. One falls in, one escapes. The escaping particle carries energy away from the black hole, meaning the black hole very slowly loses mass. For a stellar mass black hole, this process is so slow it would take longer than the current age of the universe to lose a meaningful amount of mass. But it means black holes are not eternal. Given enough time, every black hole in the universe will eventually evaporate completely, ending in a final burst of radiation. The Planck scale is where physics breaks below approximately 10 to the power of -35 meters, the Planck length. The known laws of physics stop working. At this scale, the effects of gravity become comparable to quantum effects, and neither general relativity nor quantum mechanics can describe what happens. We do not have a working theory of quantum gravity. String theory, loop quantum gravity, and other approaches have been proposed, but none have produced testable predictions confirmed by experiment. The Planck scale is not just a gap in our knowledge. It represents a fundamental limit to what our current understanding of reality can describe. What space and time look like at that scale, whether they are continuous or discrete, whether they exist at all, remains completely unknown. There is more matter than antimatter, and no one knows why the laws of physics treat matter and antimatter almost symmetrically. When energy converts to mass, it produces equal quantities of both. In the early universe, the Big Bang should have created equal amounts of matter and antimatter, which would have annihilated each other completely, leaving nothing but radiation. Instead, there was a tiny asymmetry, roughly one extra particle of matter for every billion matter-antimatter pairs. Everything in the universe, every galaxy, every star, every atom in your body, is made from that tiny excess. What caused the asymmetry is one of the deepest unsolved problems in physics. Without it, the universe would contain no matter at all. The laws of physics work the same in reverse, with one notable exception. Every fundamental equation in physics works equally well if you reverse the direction of time. Run a film of two billiard balls colliding backwards, and the physics is valid. Run a film of an explosion backwards, and the equations still check out. This time symmetry is deeply built into the structure of the laws of nature. The single exception involves a rare decay of certain subatomic particles called kaons, which behave slightly differently depending on the direction of time. What this means for the deeper structure of time itself, why we experience it moving forward, why there is a past and a future, is still genuinely unresolved. The fine-tuning problem: the universe runs on approximately 20 fundamental constants. Numbers like the strength of gravity, the charge of an electron, the mass of the Higgs boson. These constants are not derived from theory. They are measured from experiment and inserted into our equations. If any of them were slightly different, the universe as we know it could not exist. If gravity were slightly stronger, stars would collapse too fast for planets to form. If the electromagnetic force were slightly weaker, atoms could not hold together. The probability of these constants taking values compatible with life entirely by chance is vanishingly small. Some physicists argue this implies a multiverse of universes with varying constants. Others argue it implies design. So far, physics has no answer.